There are two kinds of sequences as relate to calculus. There's other kinds of sequences, but we're going to focus on convergent versus divergent. There was a series of books that was popular, I don't know, maybe 5 years ago, called the Divergent series. Did you read those?
No.
You watched the movie. Oh, movie's never as good as the book. Books are always better. Besides, the movie was only one, and right? There's only one Divergent. Oh, really?
Yeah.
I only ever. Yes, yes. Okay, so to diverge means to separate yourself from what's normal. To converge means everybody merges together, approaches the same thing, all similar. To diverge means, to be different and to separate and to not have a single value that you're approaching. So we're going to talk about that today. Before we talk about divergent and convergent, though, just want to lay the groundwork for some of the types of sequences you've already seen in your math history. So the first one we want to talk about is arithmetic. Okay, an arithmetic sequence, it follows an addition pattern. With common difference D. So the difference between every term is called the D value. That D value can be negative, so it makes it look like the pattern is subtracting, but we always say it's addition. It's adding a negative. Okay, we don't ever say it's subtracting. You're either adding a positive or you're adding a negative. So the sequence could go up or it could go down, but it always follows a pattern of addition. That's called arithmetic. Okay, then you've also worked with geometric. This was in a little bit in geometry, and then again in Ham was the last time that you did these. Okay, geometric follows a multiplication pattern. Again, we never say division. Division is always multiplied by the reciprocal anyway, so it's always a pattern of multiplication. And it's a common ratio between terms, and that ratio we call the letter R. So those are two types of sequences you've already seen. You've also seen, here, let me see. Let's talk about this first. Explicit. Okay, so an explicit sequence. That sequence is based on the counting numbers. And the counting numbers are when you plug in 1, 2, 3, 4, etc. So that's an explicit sequence. You just start with plug in the number 1, plug in the number 2, plug in the number 3, plug in the number 4. That's called explicit. And the other kind is recursive. And recursive sequences are based on the previous term. So you plug in the term before to get the next term, and then you plug in the term before that to get the next term, and that's called recursive. You need to have your calculator in certain modes if you're going to do this. So if you're going to be an explicit, it needs to be in parametric and dot mode. Can you get your calculator out a minute and take a look at so I can show you where to put those two things? Okay, parametric and dot mode. So hit mode. Okay, the fourth option down on your calculator are the options function, parametric, polar, and sequential. So you want to be in parametric mode. And then the option under that is connected versus dot. So you want to make sure that you're in dot mode and parametric mode if you're going to do an explicit sequence. Okay, and then all right, and if you're going to be in recursive mode, then you have to be in sequential mode, also with dot. And so sequential is the last one. You skip over polar and you go to sequential. We're going to do polar in chapter 11. So we will have done all the modes by the time we're done.
Can you stay in?
Yeah, dot's fine. Just sequential, yeah. There's another sequential that's like sequential and then simultaneous. That's for graphing. If you have like a y1, y2, y3, sequential means it'll graph y1 first, and then y2, and then y3. If you do simultaneous, it'll graph all of them together at the same time. So that sequential is different than the sequence mode that's above there. Okay. All right. Back to this here. Okay. So again, this is sort of review. Find the first 5 terms and T sub 75, so the 75th term. Find the first 5 and then the 75th term. Okay, and then based on the following formula. T sub n equals -1 to the n power over n squared plus 2. So this is an example. You would identify this. Oh, this is an explicit sequence. How do you know? Because it's based on the letter n. And the letter n are the counting numbers. And so you're going to plug in the counting numbers 1, 2, 3, 4, and 5, and then you're also going to plug in the counting number 75. Then T sub n would be the result when you plug those different numbers in. So when I plug in the number 1, my numerator will be -1. My denominator will be 3. When I plug in the number 2, my numerator will be +1. And the denominator will be 6. What's the next numerator going to be? Okay, and the next numerator after that, +1, and the next numerator after that, -1. So the numerator is what we call oscillating. Anytime you notice something oscillating, it's because it had -1 to the n power in it. -1 to the n power just switch back and forth. So what will the 75th numerator be? All right, it'll be -1. All right, the denominator is going to proceed according to this explicit formula. So 3, then 6. The next one is 11. The next one after that is 18. The next one after that is 27. Do you see a pattern in how those denominators are progressing? We went from 3 to 6, which was a difference of 3. And then from 6 to 11, which was a difference of 5. And then from 11 to 18, difference of, and then 18 to 27, difference of 9. So the difference is the odd numbers. That's always a squared pattern. Okay, progressing by odd numbers is always something that would come with a square. And so then working all the way to the 75th, we would figure out what 75 squared was, then add 2 to that. Did you get it? Okay. All right, so that's explicit. You're just plugging in the counting numbers. A recursive. Okay, find the first 5 terms and a sub 10. So the 10th term this time. All right, that's based on the following recursive formula. A1 is 3. AN is 5 plus A sub n minus 1. And so this is identified as a recursive sequence because it's not based on just regular n, it's based on A sub n minus 1. N minus 1 always refers to the value of the previous term. Okay, the value of the previous term. And so we don't just have n. Okay, so 1, 2, 3, 4, 5, dot, 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 up to the 10th. All right, I left a blank on this recursive sequence. What we know is that the sequence starts with the number 3. That number 3, we're not plugging in 2 for the second term. We plug in the value of 3 to find the third term, which is 8. We don't plug in 3 to find the third term. We plug in 8 to find the third term, which is 13. Okay, so this is first, second, third, fourth, fifth. We don't plug in 4, we plug in 13, which is going to give me 18. We don't plug in 5, we plug in 18, which is going to give me 23. And so in order to go to the 10th term, you can't just jump from term 5 to term 10 very easily. With one, you kind of have to figure out what's going on in between. Because I'm not plugging in the number 10. I have to know what the 9th term was before that to plug it in. And I have to know what the 8th term is, and the 7th, and the 6th, all the way down. But you can still follow the pattern as well. We're jumping up by how much every time? 5. Okay, and so I can think, all right, well, I'm going to go 23, jump by 28, 33, 38, 43, and I end up with 48 as my 10th term. Okay, any questions so far? Okay, all right. This was me giving you the formula and you coming up with the first 5 terms. What if I give you the first 5 terms, can you come up with the right kind of formula for that? So let me give you some ways to help you create your formula or construct. So construct formulas for sequences. I'm going to kind of make you a little matrix right here, a little table. First, you got to know if you're going to make an arithmetic versus a geometric sequence. So is it going to be a pattern of addition or a pattern of multiplication? Then, after that, you got to know, is it going to be an explicit versus a recursive sequence? In other words, am I asking you to create one based on the letter n or based on the previous term? So this will help you construct those different sequences. All right, if you're making an explicit sequence, the term n is found by knowing the term 1 and knowing what the additive difference is going to be multiplied by the quantity n minus 1. logically that should make sense. You're starting with the first term, and then you have to add the difference one less time than the number that you're looking for, the term that you're looking for. You have added that many differences, but one less. If you're doing a geometric one, again, you start with the first term, and you're going to multiply it by the multiplier, that common ratio, and you're going to do that n minus 1 times. If you do it n times, you'll be too far down the sequence. You'll be one spot farther than you need to be. So it's one less than what you're looking for because you're already starting with term 1. Those are explicit sequences that are based on the n value. A recursive one is a sub n. That would be a sub n minus 1. That would be the previous term plus the difference. And that would work all the way through that sequence. Whatever the previous term was, add the difference to it. And then find the previous term to that, add the difference. And you work your way through. Geometric, a sub n equals the previous term, a sub n minus 1, multiplied by the common ratio, that multiplier. So those are tips on how to construct a sequence. I'm going to give you 5 or 6 terms. You decide if it's arithmetic or geometric, and then you're usually told to make whether explicit or recursive. So we're going to try that next. So here goes it. Now, I'm not going to give you super easy ones. Okay, I'm not going to give you like, oh, the difference is 5 every time. I'll give you something that's a little bit, you got to work for it a little bit. All right, natural log 2, natural log 6, natural log 18, natural log 54, natural log 162. Find an arithmetic sequence. Sorry, find an explicit sequence. Okay, what is the commonality? Multiplying what by 3? Okay, so you're saying it's natural log of 2 times the 3 natural log 6 times 9, no. Oh, well, how do you do that? Natural log a n minus 1 like this times 3. Okay, that's a recursive sequence. I asked you to write explicit. So that doesn't work. Okay, he said something about the number 3. Okay, yeah, Brendan. Okay, so what is the difference between these? Okay, so he's saying we got to figure out the difference. So he's saying, okay, the natural log of 6 minus the natural log of 2, the natural log of 18 minus the natural log of 6, the natural log of 54 minus the natural log of 18. So these are all, how far apart are they? And so, right, what is the difference between the natural log of 6 and the natural log of 2? Okay, it's the natural log of 6 over 2, because in logs, subtraction means division, so the difference is the natural log of 3. And this would be the natural log of 18 over 6, which is the natural log of 3. And then the natural log of 54 over 18, which is the natural log of 3. So we conclude that D is the natural log of 3. So that is the common difference. And I asked you to write me an explicit sequence. So you go to explicit, starts with t sub n equals t sub 1, which was natural log of 2, plus the difference, which is natural log of 3, times the quantity n minus 1. That is your explicit sequence for this arithmetic formula, the explicit formula for this arithmetic sequence. And that will get you any term in the list. It will work all the way down. Okay, here's another one. -2, positive 4, -8, positive 16, -32. This is a little easier. Okay, what type of sequence is that? Okay, geometric sequence is based on multiplication, and I would like you to find or to write a recursive sequence formula. So, recursive starts with a sub n. Actually, recursive starts with a sub 1. A sub 1 is -2. A sub n is. Okay. So it is the previous term, a sub n minus 1, times the common multiplier. Okay, and there's your recursive formula for that geometric sequence. All right. Now we're finally ready to finish with convergent and divergent sequences. Yeah, Aubrey, question? Oh, this was okay. All right, so last thing. Convergent versus divergent. So we've talked about arithmetic versus geometric, explicit versus recursive, and now convergent versus divergent. If the limit as n approaches infinity of the sequence t sub n equals L, or that's for an explicit, the limit as n approaches infinity of a sub n for recursive also equals L. So if either kind of limit, either kind of sequence has a limit that approaches L, then we call the sequence convergent. And the converse is true. If it doesn't equal L, L has to be a number, an actual specified real number, then we call the sequence convergent. If you can't find the limit, if the limit does not exist, then it's divergent. So then the converse is true. If the limit of n approaches infinity of either t sub n or a sub n, I'm going to combine them both, does not exist, then we call the sequence divergent. So we're back to limits again. This is how calculus started, way back at the beginning, and we're back to them again. So let's do a couple limits and see what we can find out about some of these sequences. All right, let's take a look at the explicit explicit sequence 2n minus 1 over n, and prove, don't just tell me, but prove whether it converges or diverges. So your proof would be to find the limit as n approaches infinity of 2n minus 1 over n. What is the strategy when n approaches infinity and you're working with some kind of rational function like that? I suppose you could. You could take the derivative of the top and the bottom. You could also just simplify it by reducing. Okay, you divide by the highest power of n. And so that would give me 2 minus 1 over n. That's just reducing the expression. I guess you could do L'Hopital. Sure, that would work as well. But I think I could just reduce 2n over n and 1 over n. And then the 1 over n, of course, approaches infinity. So we have 2 minus 0 over 2 equals 2. So what do you conclude about that particular sequence? Right. So this is a convergent sequence. All right, final example. T sub n equals negative 1 to the n times n minus 1 over n. Okay, this is another explicit sequence, but the negative 1 to the n is going to cause this sequence to do what? Oscillate. Okay, the negative 1 to the n means it's going to switch from positive to negative, positive to negative. All right, so to prove it, we want to take the limit of this sequence, and because it's multiplication, we can split this into two separate limits. So negative 1 to the n in its own limit multiplied by the other one. Right, we can simplify using algebra again, using reducing. So the limit as n approaches infinity of the oscillating part times the limit as n approaches infinity. And if we reduce it, we get 1 minus 1 over n. Now 1 minus 1 over n is going to be 1 minus 0. But the oscillating part is going to switch back and forth between positive 1 and negative 1, and positive 1 and negative 1, and positive 1 and negative 1. So does that part have a limit? No, because it's just dot, 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 dot. This part of the limit does not exist. So because that part of the limit does not exist, even though it's multiplied by 1, the overall limit does not exist either. And so we say that this is a divergent sequence because it's multiplied by 1. So it's either negative 1 or positive 1. The values are going to switch back and forth. You could also even say that this part is negative 1 or positive 1. And when you multiply that by 1, it's still always going to be negative 1 or positive 1. There are oscillating sequences that converge, because they could be converging around 0, and that would be fine. But this is always going to be either negative 1 or positive 1 or negative 1 or positive 1, and so that would be a divergent sequence.